So, we can consider something like a ring, just a geometrical consideration, nothing has to do with the constraints possibly coming from a ring, where the atoms are oriented this way, which gives us a periodic boundary condition. So, in a formal representation, the periodic boundary condition can be represented like this: C0 equals Cn, the coefficients of the basis elements, and Cn plus 1 equals C1. So, we will go by this definition of the periodic boundary condition. Okay. So, with this, the general solution becomes e power I n theta equals 1, which means theta equals twice m pi over n, where m can take the value from 0 to n minus 1. And the corresponding normalized eigenstates can be obtained by the expansion coefficients. So, the expansion coefficient Cj for mth state can be written as 1 over square root of n exponential of I twice pi j m over n. This is the coefficient. The eigenvalues would be given as E equals alpha plus twice beta cosine of twice pi m over n. Now, if we go to the limit n tending to infinity, you can see that theta represented this way becomes a continuous variable, and the eigenvalue will have a continuous spectrum. So, at the energy eigenvalue is always alpha plus twice beta cosine of theta. This quantity becomes a continuous spectrum when n tends to infinity. How can we plot this quantity? This is theta axis and this is the energy axis. It would look somewhat like this, a cosine function, where we have plotted it over minus pi to pi, the value of theta, which is in the first Brillouin zone of the system. The maximum value of energy here becomes minus alpha minus twice beta, and minimum value of energy here becomes alpha plus twice beta. And the eigenstate of this infinite ring that can be, so if we consider an infinite periodic system, The eigenstate can be represented by Cj's, the coefficients. This would be 1 over square root of n e power I j theta. Here we can examine the states and comment that at theta equals 0, we will have the maximum bonding state, corresponding to this eigenvalue at the bottom of the spectrum. At theta equals plus minus pi, which is the boundary of the Brillouin zone, edge of the Brillouin zone, there we will have the maximum antibonding state. And at theta equals 0, we will have neither bonding nor antibonding, that is non-bonding state in this continuous spectrum. Now, since theta specifies the energy and the expansion of the eigenstate in terms of the basis states, it is appropriate quantum number for an infinite number of atoms and periodic boundary condition. And if this is the spectrum in terms of theta, can we find out the density of states for this kind of a system? The density of states can be given as d as a function of energy, which is the derivative of the number of states with respect to energy. And we can write theta equals the crystal momentum times the distance between two hydrogen atoms, that is the lattice constant. Why can we do that? If you go to the definition of reciprocal axis vectors, then you can understand this easily. Here theta had the range from minus pi to pi, and within the first Brillouin zone we will have a certain range for the vectors in the reciprocal lattice, and that would be precisely k times a, and if k times a becomes minus pi, that is one edge of the first Brillouin zone. If it becomes pi, that is the other edge of the first Brillouin zone. So, in the reciprocal lattice, reciprocal space, this Ka is the form of theta for one dimensional Brillouin zone. For more than one dimensional, it would be a vector. Okay. So, this quantity, density of states, can now be written as ds dk times dk dE, the absolute value of this, which is nothing but ds dk over dE dk. dE dk is the gradient of this energy band, energy dispersion that we have plotted here, because this axis is k now, it is theta equals Ka. So, we can calculate for a cosine function this quantity very easily, and we can write that this quantity would be equal to twice n a over twice pi 1 over 2 beta a sin Ka, which is simplifies to n over pi 1 over 4 beta squared minus e minus alpha squared and square root of this quantity. This is the density of states for the entire system. Now, if we want to find out the density of states for one atom, we represent that with small d. It is not the differential, the density of states for each atom. This can be represented just by removing this n from here, 1 over pi 1 over square root of 4 beta squared minus e minus alpha squared. And if we plot this density of states, we will obtain the following. We will get this kind of a picture where it asymptotically reaches here and here. This is the energy axis and this is dE, the density of states. The middle point is alpha, extreme left is alpha plus twice beta and extreme right is alpha minus twice beta. You can see from here, sorry, this is not minus. So, alpha minus twice beta is here, alpha plus twice beta is here, and these are the places where the density of states peak, and in between it is very flat. There are very few states in the region in between. That is what we obtain by performing this calculation.